postdoc at the Laboratory for Industrial and Applied Mathematics at York University. She's done a lot of work related to epidemiology and together with John Hong, has a lot of interesting results and that entire research group. Today, she's going to speak about a renewal equation model for disease transmission dynamics with contact tracing. Francesca.
Thank you very much. Thank you very much for the invitation to speak here. I'm really happy to have this opportunity. And first, let me introduce my collaborators for this project. My supervisor, Professor Jianwen Wu from York University, and Lorenzo Pellis from Manchester, and Dr. Ogden from the Public Health Agency of Canada. And I want to acknowledge the Canadian Institute of Health Research for the funding for this project. And regarding this project, there's actually a preprint available on medRxiv about this contact tracing model that I'm going to present. And I'm going to talk about contact tracing, which is as we all know from this pandemic, as we all have learned, is the process of identifying and isolating the individuals among the contacts of one confirmed infected case. And the aim is to stop as many infection chains as possible, as early as possible. And there are different possible strategies of contact tracing. One is forward tracing. When one infected individual is found, the search is among the secondary infections of this case, whereas backward tracing aims at going back to the infector, the original infector of the index case, while full tracing combines both strategies. So we go backward, try to identify the infector, and then search also for the secondary cases. So these are the type of strategies that are normally considered. And the project originally started as a challenge, let's say from my supervisor, Professor Wu, that back in the spring during the first wave, told me, well, you know, Francesca, there are no correct models for contact tracing in the literature. And why he said that is because he said there are no correct models for contact tracing because contact tracing takes into account the relation between infector and infected. One individual is determined, is identified, depends on the detection of their infectees or of their infectors. And this essentially involves some delayed, so involves going back and forward in time. And there are no models that can correctly capture this relation. And indeed, there are many challenges in modeling contact tracing. Besides needing to describe the underlying infection spread and some other screening or diagnosis program that can actually initiate contact tracing. But the most difficult thing is to model the contacts between individuals and the possible and the infection transmission. The most difficult thing is that when one individual is detected, their contacts are distributed in the past. And during this time, they have already progressed through the disease stages. So they have already possibly have developed infectiousness, and possibly they have generated new infections. So because of this complication, most studies are based on stochastic agent-based models. Indeed, because agent-based model can allow to keep track of each single individual in the population. So for each single individual, at each time, the transition through the different stages of the infection is described, and all the infectious contacts are kept. So it's kept track of all the infectious contacts. So these are the models that are most often used to study the effect and the effectiveness of contact tracing for disease control. Other types of models are branching processes or network models, and especially mean field approximation of network models. why classical compartmental ODE models fail to correctly describe contact tracing is because they fail to capture the details of the contact's distribution over time. So ODE models cannot, or it's very difficult to incorporate in ODE models the idea of this distribution in time of the contact, so contacts that happened in the past and then they have already progressed through the stages. Now, so we have tried to approach the problem from the point of view of structured population models. And what I want to do in the talk is really to focus on the modeling approach that starts from the individual level and then lift the processes from the individual level to the population level. I think this is a very interesting and powerful approach. And so I will try to describe how the model was developed. And then I will conclude with some applications to COVID. Maybe I will not give many answers to COVID-19, but I will try to show how this type of model can help getting some important insights insights about the epidemic and about the contribution of diagnosis and contact tracing to control the infection. So the model I'm going to present is a classical SIR type model. So the population is divided into 3 classes: susceptibles to the disease, infected and infective. So they have contracted the disease and they can infect others, and then removed individuals that are either recovered and permanently immune, or they have possibly been isolated, so they are not infectious anymore. And then I will consider 3 main processes: the standard infection and recovery process, the diagnosis from symptoms, and the process of contact tracing. I will work under some simplifying assumption in order to introduce the modeling approach. First, I will focus only on forward contact tracing. So when one individual is detected, the aim is to find the secondary cases of this individual, so the cases that have been infected by this person. I assume that upon diagnosis or tracing, one individual is instantaneously isolated, and isolation is perfect. This means that after isolation, individuals are not infective anymore. And I also assume that tracing is instantaneous at detection of an individual. So in this phase, I ignore tracing delays, although they can be included easily in the framework. And this also means that tracing is iterative in the sense that contacts of contacts are iteratively traced and instantaneously traced. Then I will assume that not all the contacts are found. So I will assume that there is a fraction that I call epsilon with subscript C of contacts that are actually traced, but another fraction can escape tracing, possibly because not all contacts can be reached, or because individuals do not disclose all of their contacts, or because some contacts are simply unknown. And then I will work under the assumption of homogeneous mixing and assuming that all individuals are identical to each other. So these are the basic assumptions. And here is a scheme to try to give an idea of how the contact tracing works in a infection network. So if we go from left to right, this is chronological time. And if we assume that we start with an initially infected case, so we assume that this case, for example, generates 2 new infected individuals. These are individuals 2 and 3. That possibly can generate more infections. Like, for example, in this case, individual 3 has generated 2 more infections that all progress through time. Then the idea is that if this initially infected individual is diagnosed at some point in time, because possibly he has developed symptoms and it has been hospitalized and it has been diagnosed and isolated, then instantaneously at the same time, contact tracing is initiated for all its secondary cases. So all secondary cases, this individual 2 and 3 are traced, and iteratively their own secondary cases. So also this individual 4 and 5 are traced. But so if they are actually traced, they are isolated and they do not contribute to the force of infection anymore. They cannot infect anyone else. But some individual may escape tracing. So for example, this individual 5 escapes tracing. It's not detected, and more infections can be generated until possibly this individual is diagnosed itself. So this is a schematic idea of the relations between the two processes. And as I said, so I will focus on in a deterministic context. So I want to develop a deterministic model. And I want to work in the context of structured population models. This means that I want to start by describing the processes at the individual level. So given an infected individual, I want to define the parameters of the different processes in terms of the age, what I call age since infection, which is the time since the infection event. And I will also write ASI in brief. But and also I want to mention that whenever I say age, I will mean age since infection. There is no demographic age in the model. But the idea is that to each individual, we can prescribe epidemiological parameters or parameters related to the diagnosis or contact tracing. So for example, to each infected individual, an infectivity function that describes the infectiousness or infectivity of an individual as a function of the age since infection, an incubation period, which is the time to symptom onset, and a diagnosis rate or diagnosis probability, and a contact tracing rate or probability. These are the probability that an individual is diagnosed or traced given a certain age since infection. And when I first started this project, after I accepted the challenge of trying to build a rigorous model, I was going through this list and I thought, okay, infectivity, this can be found in the literature. If I think at COVID literature, there are several estimates of the infectivity profile with respect to the age since infection and the incubation period with respect to the age since infection. And the diagnosis rate can also, so diagnosis rate depends on the diagnosis strategies. But for example, if the diagnosis is upon symptoms, one can assume that this diagnosis probability is very much related and connected with the probability of developing symptoms. So this diagnosis rate could be linked to the incubation period in some way. Then what about the tracing rate? Tracing rate, I really had no clue how to describe the tracing rate, because the probability that an individual is actually detected depends indeed on what happened to the infector. And the relation between infectee and infector changes when the epidemic progresses. Like if there are more or less susceptibles in the population, it's more or less easy to generate new infections, dynamical quantity, and it's really difficult to describe. So I thought, okay, I know nothing about this tracing rate. I will just consider this as unknown and try to describe indeed how this rate behaves. So this will be the unknown in the model. And I want to focus a little bit more in this on these last two processes. So first, how the diagnosis process is modeled. In the model, this is assumed to be known, and this is because it's determined either by the epidemiological parameters, like for example, the incubation time or the probability that a test results positive and so on, and by the screening policy that can be testing of symptomatic individuals, but it can also be, for example, random or random testing or mass testing. But once this policy is given, we can assume that the diagnosis process is given. And when I say it's given, I mean that I prescribe a certain rate at which individuals are diagnosed. And given a rate, I can define the probability by multiplying the rate times the differential, the infinitesimal element dt. This is the probability that an individual is diagnosed in an infinitesimal interval of time. And from the rate, I can also define the probability that an individual has not been diagnosed before a certain age tau. This is given by the negative exponential of the integral of the rate. And this is in math, it's also called survival probability to diagnosis. And I will assume that the diagnosis process is independent of time. In reality, these policies can change in time, but I will ignore this possibility here. Then contact tracing is more complex to describe, as I tried to say before. It may be time dependent because it depends on the underlying epidemic. And indeed, it cannot be prescribed a priori, so we take it as unknown. And similarly, as for diagnosis, we define a certain rate at which one single individual is traced at a certain time at a certain age. And then this defines the corresponding probability that an individual is traced in an infinitesimal interval of time, and the probability that this individual has not been traced before a certain age. And this is very similar as in the diagnosis process. The only difference is that because there are two variables here, time and age, we have to integrate along the characteristic lines. So we have to somehow integrate along the diagonal in the time-age plane. But the concept is really similar to the diagnosis process. And then because the two processes are independent, diagnosis and contact tracing, the probability that an individual has not been isolated, either by diagnosis or tracing, this is simply given by the product of the two probabilities. And okay, so now I'll go into the description of the model. For some further notation, I will call n and with subscript 0 the total population, which is assumed to be constant. And y will denote the incidence at time t. So just a reminder that y times the differential element dt is the number of newly infected individuals in the infinitesimal interval of time. And the capital S denotes the number of susceptibles in the population. And this can be described from the incidence, because the change in the number of susceptibles is given by a negative the incidence. So we have this relation between the susceptibles and the incidence. And the last important ingredient is the total force of infection at time t. And the force of infection is such that the incidence at any time is given by the force of infection times the fraction of individuals that are susceptibles in the population. So this is the basic relation between the incidence, so the number of new cases, and the force of infection. And we will use this relation to obtain an equation, a closed equation for the incidence y. Now, recall that I called beta the infectivity of one individual, one infected individual. Then we can express the force of infection in terms of the incidence by summing the contributions of all the infected individuals of a certain age since infection. This is a very standard approach in epidemiology to link to obtain an equation for the incidence. And the total force of infection is given by summing up all the contribution of each age that can go from 0 to infinity. We count how many individuals have age since infection S, and this is given by how many individuals were actually infected at time t minus S, this term here. These individuals are infective only if they have not been isolated yet. So we multiply times the probability that they have not been isolated. And then we multiply times their individual infectivity, beta. So if we plug this into the equation we had before here, we get the standard renewal equation for the incidence here. So remember that S can also be expressed in terms of the incidence. So this is our renewal equation for Y, but we still need to prescribe the survival what I call survival probability, calligraphic F, which is the probability of not being isolated yet. And this is defined through the unknown rate HC. So we're going to prescribe an equation for HC. And as I introduced before, the rate times dt denotes the probability that an individual is traced in an infinitesimal time interval, given that the age since infection is tau. So this individual was infected at time t minus tau. And we can break this down because one individual is traced if their infector was detected. So I multiply the probability that the infector was detected at time t times the probability that the contact is actually traced, because some of them may not be identified. So this first term here we called epsilon c, and the second term depends on the infector. But the parameters of the infector are completely characterized by the age since infection of the infector. So we break down this one probability by the infector age since infection. So we condition on the age of the infector. If I look at a diagram, if we are describing the probability of this index case being traced, this index case has age since infection tau at time t. This depends on the probability of the infector being detected. And what we want to do now is to go back to the infection event at time t minus tau, study and consider all the possible age since infection of the infector at time t minus tau, and then relate the probability of the index case being traced with the probability of the infector being detected. So this is schematically what we should do to break down this probability here. So what we get is, this fraction is actually assumed to be constant, epsilon, so I put it here, and then I integrate over all the possible ages of the infector. And then I multiply the probability that the infector has actually a certain age S times the probability that the infector is detected, and therefore contact tracing is triggered and the index case is detected. Now, maybe I can go a bit faster here, but this probability can be written in terms of the survival probabilities and the rates, detection rates of the infector. But then, this term here should somehow be described as well. So I will focus on this one term here that I call psi. So psi is the probability that an infector has a certain age since infection S when we know that the infection event happened at a certain time t. So this is equal to the number of infections from individuals of the age since infection S over the total number of infections in the population at time t. And this is proportional to the contribution, to the ratio between the contribution up to the force of infection of individuals with age S over the total force of infection. So we were able to express also this psi in terms of the incidence and the force of infection. And actually, we can express the force of infection in terms of the incidence. So we can finally get an expression in terms of the incidence only. Now, this is the derivation, and this is the final model. So the final, if we put everything together, what we get is a system of two integral equations. The first one is an integral equation for the tracing rate, and the second one is the renewal equation for the incidence. And the system is closed because the survival probability here can be expressed in terms of the tracing rate, and the number of susceptibles can be expressed in terms of the incidence. So this is a closed system of two equations, and it describes the full epidemics dynamics. What is very interesting of this equation is that it is delayed in time. So we have delayed arguments here in the incidence in both equations, and it is advanced in the age-since infection in the sense that the variable at the age-since infection tau is described by the value at later ages. But it may seem complex, but actually it can be solved using standard numerical methods, for instance, quadrature rules. So this is actually, because it's just two equations, it's actually very convenient to simulate and to analyze. And that's all what captures the full model. Now, one question is, okay, we have a system in terms of the rate, HC, but this is really hard to measure in practice. Like, we have no idea of how to measure the individual probability of being traced. But in fact, we have all the ingredients to compute the concrete quantities of interest that can be measured in practice and can possibly be used for fitting a model. For example, we can express the number of individuals that are diagnosed at a certain time, and we can express the number of individuals that are traced at a certain time. So if we can get data about these quantities, we know exactly how to relate these quantities to the variables of the model. So it's less abstract than it seems. And then the model was constructed in the full nonlinear, for the full nonlinear epidemic, but we can focus on the very initial phase when the population is assumed to be completely susceptible, and we ignore the depletion of susceptibles. Then the incidence is exponential, approximately exponential, with a certain exponential rate R. And then if we plug this assumption into the previous system, it simplifies, and what we get is Lotka-Euler type equation for the growth rate R. This is quite standard in epidemiology. And this is coupled with an integral equation for the tracing rate, which is now independent of time. So this is a stationary process in time. And what I find interesting is that this equation that describes the contact tracing is still nonlinear in HC. So this is a nonlinear equation because this function here is an exponential. And indeed, this captures the fact that even in the linear approximation at the beginning of the epidemic, the contact tracing is essentially nonlinear because it is essentially based on the contacts between individuals. So it's a second order process. And the other very interesting thing is that the reproduction numbers can be expressed with explicit formulas. So by solving the system, we can compute explicitly the reproduction numbers. And I use the plural because we can define the basic reproduction number without intervention, or the reproduction numbers with diagnosis, or with diagnosis and contact tracing in place. And so the important thing of having explicit formulas is that we can get general insight. So for example, it's straightforward to show that the epidemic is under control if the fraction of transmission So the fraction of the function beta, of the area under beta, that occurs before isolation is less than 1 over R naught. And this is independent of how isolation is achieved, if it's either by diagnosis or by diagnosis and tracing. Now, so I want to conclude with some analysis we have conducted with parameters from COVID-19. And so the goal is really to show how having two equations that are deterministic and fast to simulate can allow to obtain many type of analysis in a very efficient and flexible way. And I will focus on different types of the effect of both diagnosis and tracing in the control of the epidemic, in particular in terms of diagnosis coverage, so how many individuals can be diagnosed, and the delay between the symptoms and the diagnosis, and then the tracing coverage and the tracing window. By tracing coverage, I mean how many contacts are effectively traced, and the tracing window, I mean the number of days back in the past during which contacts are traced. So when I detect an individual, I can search contacts up to 2 days ago, 3 days ago, or 5 days ago. Then we also investigated the consequences of short-term interruption of contact tracing when the resources are limited. So for the simulation, I have fixed some parameters, indeed related or from the literature about COVID-19. So I've taken the incubation time distribution and the generation time distribution from the literature. And the infectiousness is related to the generation time distribution via R naught. And the diagnosis rate is related to the incubation time distribution because we assume that there is a fixed delay between the symptom onset and the diagnosis that I will fix from time to time. So now, the first plots I want to show, they really show how having explicit formulas for the reproduction numbers allow to obtain very efficiently, to perform some scenario analysis and to explore some properties very efficiently. So this is a chart that describes, so where each point describes some effectiveness of diagnosis. So on the x-axis is how many individuals can be diagnosed. And on the vertical axis is the delay from symptom onset to diagnosis. And then these colored lines represent the boundaries between the region where the epidemic is controlled and the reproduction number is lower than 1. This is what happens in the lower corner. And above these lines, the epidemic is able to spread. And then different lines correspond to different tracing efficacy. So the orange line corresponds to all contacts being traced immediately, and the yellow to 80% of the contacts traced, and so on. And here we can see that only very effective diagnosis, so very fast diagnosis with very short delays, can allow control if contact tracing is in place. This is obtained with an R naught of 2.5, which is close to what estimated at the beginning of so for the unconstrained COVID epidemic. If R naught is lower, so it's 1.5, which represent a case where there's already some physical distancing in place, for example, then the situation improves a bit in the sense that the lines move up. So we have a larger region the epidemic can be controlled. And even with diagnosis only, so with no contact tracing, this is the blue line here, we could be able to control the epidemic, but for very, very short delays. Yeah. Another type of analysis we could perform is the effect of the tracing window. So how many days back from detection of a case we search for contact. And for a set window, so 2 days, 3 days, up to 5 days, we can understand what's the tracing coverage, so how many contacts we need to find in order to reduce the reproduction number below 1, so to gain control of the epidemic. So maybe this doesn't give answers, but it's just a proof that we can really investigate many aspects of the tracing strategy. And what I find interesting is also to see the profile of the solutions that we compute. So here in the upper panel, I have plotted the solution of the tracing rate that is found for a contact tracing window of 2 days or 3 days or up to 5 days. So this represents the individual tracing rate as a function of the age since infection. And here on the right, I have combined the rate of being traced or diagnosed. And what I find interesting is that the effect of tracing is really to improve the probability of being isolated at the very beginning of the infectious period. So when the age is small. Of course, this depends also on other underlying assumptions. Like here, we have assumed that there is no tracing delay, and there's no, well, and it depends also on the tracing coverage, like how many contacts are effectively traced. But indeed, the goal of contact tracing is to detect as many infected individuals as early as possible. Whereas if we rely on symptoms only, we can, so this probability of diagnosis is very delayed. And I won't focus on the lower panels, but they show the same information in terms of the cumulative distribution function. Now, this is another example of analysis that we could perform with the full nonlinear model. So here we have simulated an epidemic. I focus on the first row. The upper panels show an epidemic that is declining with contact tracing, and the blue line shows the incidence, whereas the red and yellow lines are the number of diagnosed and traced individuals at each time. And with contact tracing, this epidemic is controlled. This is declining. But then we wanted to study what happens if we interrupt contact tracing for a certain period of time. So we set to 0 the number of traced individuals. And in this case, without contact tracing, the epidemic starts growing again. But then if the interruption is limited, so if contact tracing is resumed at some point, we can still control the epidemic after a while. So we resume the initial decline, and this is summarized on the right with the estimated growth rate. So the estimated growth rate is negative at the beginning with contact tracing. It jumps positive during the interruption of contact tracing, but it goes back to negative when contact tracing is resumed. But then in the lower panel, we have shown that if the interruption of contact tracing is a bit longer, and if we assume that there is some bound to the tracing capacity of the system, so there's only a limited number of individuals that we can trace at each time, then if the interruption is long enough that this capacity is breached, then we will never be able to resume the initial decline. So for example, in the right, you see that we are not able to bring the growth rate back to negative values. The growth rate will always stay at positive values. And this analysis would be important in the case when it's necessary to decide where to focus the efforts and the resources for contact tracing, because there are So with low incidence, so if the incidence is low, as in the upper panels, contact tracing really can make the difference between control or spread of the epidemic. But if we let the incidence grow a bit larger, so that it's not so that the resources for contact tracing are not enough to cope with the numbers of infected individuals, then contact tracing is not sufficient, loses power somehow. And okay, I don't want to spend too much time on this slide, but this is work in progress to compare the deterministic prediction that we obtain with an equivalent agent-based model, which is, as I said, most contact tracing models are nowadays formulated as agent-based model. So we have tried to compare our simulations with a standard agent-based model. But maybe I won't put too much time in this slide. And then just to conclude, I want to summarize some of the strengths and some of the reasons why I really love this model. Is because, first of all, it is obtained by lifting the individual processes to the population level. And this means that every term in the model has a precise interpretation in terms of the individuals. And the age-since infection structure allows to incorporate realistic distributions of the important parameters like infectiousness, incubation period, or recovery time. Moreover, it is deterministic. It is fully described by the two equations. So this means that it's quite easy and fast to simulate. And this is very convenient, especially when simulations should be repeated many times, for example, in parameter estimation. We haven't done this yet, but this is one of the things that we hope we can do, like use the model to actually to fit so if we would have more precise data about how individuals are diagnosed from symptoms or traced, then hopefully the model could be fitted to data. And a deterministic formulation also allows a more transparent relation between model parameters and output. Now, there are many limitations that we hope to address. And the first and maybe most important one is that it is context of homogeneous mixing. So it ignores any clustering due to households or super spreading events, which are shown to be very important in the context of contact tracing. We have assumed for simplicity instantaneous contact tracing, but this is an assumption that can be easily relaxed. And something that is quite important too is the relation between infectiousness and incubation period, which are now assumed to be independent of each other, but this may not be realistic. And indeed, often the infectiousness of an individual is described in terms of the symptom onset. One comment is that the model now accounts only for the tracing of infected individuals. So we have ignored the fact that some healthy individuals may be traced and quarantined. And this maybe is not relevant for the spread of the infection, but it's very important for evaluating how disruptive contact tracing policy is to the society. And then, I have presented the model for forward tracing, but then we plan to apply the same framework to backward and full contact tracing. So that was all what I had presented. I hope I conveyed the idea of the modeling approach. And I want to thank you again, Professor Murthy and Jianong Wu for the invitation, and thank you everyone for listening.
Thank you, Francesca. So I'm very glad you mentioned Professor Moody. So on page 25th of your slides, so that problem, I gave you a mathematical problem, but that problem of how damage can be done if the contact tracing fails at a certain stage due to the resource limit. It's something coming from the Ontario Science modeling consensus table from multi. So so that is a real problem to motivate from what happened in some part of the country. Now, I want to also thank the audience. We have larger audience today from different parts of the world, and very glad they all stay until the very end. It's a very disciplined audience. With that, I have questions. Anybody want to ask a question can raise the questions. You can raise your hand, ask the question directly, or you can post the questions through chat.
Looks like it was such a clear talk, nobody has questions.
So I have a quick question from the audience. Is about you mentioned that we talk about there's no model for correct model for contact tracing, but I think there are some new development over the next few months.
Yeah, so that was a bit exaggerated. Like, yeah, that was maybe exaggerated as a comment. So I didn't find a similar model for the full epidemic. I found models for, well, beside all the agent-based models, and those are correct for sure for how they are constructed, but I only found models for the linear case, because they're based on the generation perspective, so looking at each generation of infection. And I have found models based on networks that normally are solved using mean field approximation. Now, I may have missed something in the last months, and I'm very happy if someone can give some more references.
I just want to mention that we have already invited Joan Muller from Munich, from Germany, to talk about the most recent work as well. And I think you will hear from the European group.
Yeah, and a similar approach, has been applied for the generation perspective. So looking at each, so at the generation perspective, but this cannot describe the full nonlinear epidemic because it doesn't describe how generation mix with each other.
Thank you. I have a question from Mark Penny. Mark, do you want to raise a question directly?
Sure. Can you hear me?
Yes.
Okay. Yeah. Excellent. It was a very interesting talk. My question was, how much do you think that if you dropped the homogeneous mixing assumption and introduced a certain amount of heterogeneity in number of contexts, that this would lead to large differences in the predictions for forward or backward tracing? The sort of naive intuition I have is that, especially for backward tracing, you'd expect that if there was a person who had a large number of contacts and therefore generated a large number of secondary cases, you'd have a lot of repeat identifications of sources of infection. And I don't have the same intuition for forward tracing, but I wonder if you had any thoughts about it.
Right. So I'm sure it would make a difference. And I think one quick way to study this situation in the framework would be to use like maybe two groups with different number of contacts. Mm-hmm. But and I'm sure it makes a difference because I'm aware of where that actually have studied the effect of clustering, especially in backward tracing, as you say. I'm not sure if I'm able to answer if I have more intuition on the forward tracing.
It was only a partially fair question. It wasn't something you had modeled, but I was curious to pick your brain.
Right. So I believe it is an important aspect, but I wouldn't right now. I haven't considered this. I haven't thought carefully enough about this yet.
Yeah, excellent.
But thank you for the remark, because that's something that cannot be excluded from the study of contact tracing.
Thank you. I have a next question for Andre Pugliese from Italy. Andre, glad you're here. So are you able to raise the question directly?
Yes, okay. Hello. Well, very nice talk. It was very interesting. I was it was a bit fast to really follow everything. So I was wondering, when you compute the tracing probability and you look for the probability that the infector was detected before that time, doesn't that probability depends also on the tracing policy? Because perhaps it's more likely that it depends also on that. I'm not sure whether this is exactly independent. When you have the probability that is detected, that depends also on age. Is that correct?
Right. So you mean when I calculate, when I make this calculation, or when I?
No, in this calculation, it was
okay.
a bit.
Yeah. So the idea is that. So for sure, it depends on the tracing policy. So now I'm considering forward tracing. So each individual traced only from their infector. And now the thing is that so it does depends on the infector and on the age since infection of the infector, and this indeed comes into the equation as the unknown that we are trying to model. So I'm not sure if this answers your. I'm not sure if this answers your question.
Yeah,
Thank you.
Give me some more time to look at the slide.
Yeah, I know. It was actually very difficult to choose how to present this equation, because I think it's at the same time very complex and very easy. But it's easy only if one has enough time to look at it. And but yeah, so the idea is that this depends on the age of infection, age since infection of the infector, and this is the unknown. So this is why we get the advanced arguments in the equation.
Okay.
I hope this answers, but thank you very much.
It does. I will look again more carefully, but it does more.
Yeah, thank you.
Andre's question is whether the detecting probability and the tracing process are truly independent. I think that's the issue.
Well, that's another big question. So that's another good question, an important point. And they are independent because the diagnosis is really only depends on the individual age since infection, and about nothing else in the population. Whereas the tracing process depends on the detection of other individuals, but not on the individual itself. So it's something external. Somehow, yeah, we have thought about it a lot. So maybe it's difficult for me to explain now. Give me 1 second.
My answer to Andre's question is, in theory, in the formulation, the detection probability and tracing probability, those are independent in theory, but in practice, of course, that's different. How you're going to trace and how to detect, they are targeted. So they are not, in practice, they're not independent.
Well, the idea is that they are not independent, and indeed, this is why we have this construction that links one to the other. So the diagnosis probability is given, so that's independent that's independent of the underlying epidemic, but the contact tracing does depends on the diagnosis of the infector, and this is what this computation is linking.
All right, so the paper should, the full paper, the final version should be on the Royal Society website very soon. So the template is already online. So I think we'll have time for people can look at the templates, and the presentation is recorded. So we are welcome to revisit it. And with that, and Kumar. I don't know if I have other comments.
Very nice talk, and thanks everybody for coming.
Thank you. So thank you.
Good.
Thank you. Thank you very much.
Thank you.